I wanted to make a short video describing my solution to the latest quiz that we had. That quiz was about graphing a function, a polynomial function that's in factored form. And so I gave you this function, f of x equals x plus 2 squared times x minus 1 to the third times x minus 5. And we want to sketch a graph of this, so we don't have to draw a perfect version of the graph to scale, but rather a sketch that shows all of the major features of the graph. So I'll begin by just drawing a nice set of x and y axes. And I'll also begin by reminding you that we like graphing polynomials that are in factored form because it's very easy to see the roots. We can just look at the equation and figure out what values of x are going to cause this function to give a value of 0. And that's what the roots are, or we call them the zeros sometimes, and they basically give us the x-intercepts of the graph. Notice that if I put -2 into this first factor, it gives me 0. Regardless of what the other factors give me, the product of all these factors will also be 0, so the equation will return 0. So there's one of the roots at -2. We have another root at 1, x equal to 1, because 1 causes this factor to be 0. And when I find the product of all of these factors, regardless of whatever these two give me, the product will be 0. And then the last factor gives us a root of 5. So I know that my graph somehow interacts with the x-axis in these three places. Now I'm left to figure out how to draw the rest of the graph. And of course, there's a lot of different ways to draw a nice, smooth polynomial curve through all of these 3 points. But I need to do a little test to figure out exactly how to begin. I'm going to start by choosing a number on this interval, x values from -2 down to -infinity. If I just know whether these values in this interval make my function positive or negative, I'll know whether to start on the positive side of the graph or on the negative side of the graph when I draw. So let me figure that out. I like to expand my function. So I'm going to write out every single factor. Okay, there they are. There are 6 factors. And I'm going to imagine if I put -3 into this function, what would I don't care about the numerical answer when I put -3 into the function. Instead, I really just care about the sign. Is it positive or negative? So again, I can look at each individual factor, and if I put -3 in for x here, it's going to give me -1, right? And both of these factors will give me negative. These 3 factors will also give me a negative value if I put -3 in for x. And the last factor will give me a negative value. 1, 2, 3, 4, 5, 6. Well, you multiply 6 negative numbers, it's going to give you a positive number. So I know that on this interval, my graph is positive. Now, I also know that I want to identify the coordinates of my y-intercept because that's an interesting point, and I'd like for my sketch to include it. So I know that the way I can find the y-intercept by putting 0 in for x, and that just so happens to be an x value that's on this next interval. So if I figure out the actual y-intercept, I'll know whether my graph starts up here in the positive region and if it goes back this way or if it goes across the x-axis into the negative region, depending on whether my y-intercept is positive or negative. So let's just imagine plugging 0 into all of these factors. I would get 2 times -1 times -1 times -1 times -1 times -5. And that, if you multiply that out, you'll see we get 20, positive 20. So my y-intercept is positive which means my graph must come down and go back up this way. Let me just draw that behavior near the root. It looks like this. And that should make some intuitive sense to us because we're squaring this factor. And we have a multiplicity of 2, which is an even number. And we're getting this parabolic behavior near the root. And it's because of that exponent right there for this factor. Now I could keep going. I could test a value of x like maybe 2 or 3, some value of x in this region. And I could test some value of x on this interval like 6 or 7 and see what happens if my graph is positive or negative on those locations. But I can also just use the multiplicity to figure it out. Here at this root, the multiplicity is 3. So I know that because it's odd, my graph is going to cross the axis. It's going to come from the positive side and it's going to go to the negative side. But also because the multiplicity is 3, I know that I'm going to get this inflection point near the root. The graph is going to flatten out as it approaches the root and then turn and get really steep as you get farther away from the root. And that's the nature of the graph. This is how the graph behaves because of that multiplicity of 3. I've gone from the positive side to the negative side. That's because it's odd. And I've added this little inflection because it's not just odd, but it's 3. It's more than 1. See, this root has a multiplicity of 1. And I know I'm already down here in the negative region. I'm just going to cross the graph, the x-axis, right at that root, rather than inflecting across the x-axis at that root. So now what I've done is I've indicated the behavior of the graph near these 3 roots. So now I'm left to just kind of connect them. So I'll come down this way, and then I'll come up and meet my behavior at where x equal to 1, and then come back up through here and keep going. And look, I put arrows on the ends of these roots. I put arrows on the ends of my graph to indicate that it keeps going in both directions forever. These are not endpoints. This graph continues. So that's my graph. It looks pretty good, but I'm going to just label a couple of important attributes of this graph. First of all, I already found my y-intercept, and I discovered that the coordinates of that y-intercept are 0 for x and 20 for y, so I'm going to label it with the coordinates. And I also want to locate these minima and this maximum and just say that I know what they are. So when I say label these, this is really what I mean. This is a relative minimum. Okay, it's relative because it's sort of a local minimum. It just happens in this area. Surely the graph goes lower right here. This is the absolute minimum because the graph does not go any lower than that. That is the lowest point on this entire graph. If you put x values in from negative infinity all the way to positive infinity, this will be the lowest value that you get from this function. And lastly, we have a relative maximum, okay, right there. And it's relative because clearly the graph continues up to positive infinity at this end and at this end. So this is not the absolute maximum. The graph definitely goes higher, but it's a local maximum. So we call that a relative maximum. So what we have here is a complete graph of this factored polynomial. I began by drawing my axes and then finding the roots and labeling them. And then I determined the sign of the graph on each of these intervals. That is, whether the graph is positive or negative. And I drew the behavior near the roots. And I used the multiplicity to think about how the graph behaves near the roots. And then I just connected them with a nice smooth polynomial